we're now in this awkward period of time where we've completed the stuff that you need to know for the upcoming exam, but we're going to talk about new stuff that you don't want to care about yet, and that's fine, but you will soon care about. So just do your best to open up a new drawer of knowledge in your head, and we'll start in on that. And if you need to not worry about it today, that's fine. You can come back and rewatch the lecture and move ahead. It always feels, life is going to feel increasingly like this. You guys probably have seen the 2000, was it 3 or 4, classic Christmas movie Elf with Will Ferrell. And you know how Santa Claus at the North Pole says, we've had a very successful year, never another very successful Christmas, and now it's time to start preparation for next Christmas. And the elves cheer and they get right back to work, right? This is how the rest of your life's going to feel, so congratulations. All right, so we're going to deal with elimination reactions. We're starting in on chapter 8 today. And I tried to set this up last time by showing you the consequences of hyperconjugation, both in the starting material for an SN2 reaction, which is the molecule with the leaving group, and the intermediate for the SN1 reaction, which is a carbocation. We talked about hyperconjugation, and this is where a filled orbital on the beta carbon, the one that's adjacent to the carbon with the leaving group, lines up with and engages in side-to-side overlap with an empty orbital on the alpha carbon. In the case of the starting material for the SN2 reaction, that empty orbital is the sigma star. In the case of the intermediate for the SN1 reaction, that empty orbital is the p orbital on the carbocation. And the consequences of hyperconjugation are basically two. First, the electrons in the adjacent CH bond spread out towards the empty orbital. That's stabilizing because it involves delocalization. And the second consequence is that the LUMO, the empty orbital, spreads out onto the adjacent atom. So if you were to look up what the LUMO looks like for this alkyl halide, you would see that most of it is the sigma star, but there's some additional LUMO on the adjacent hydrogen. And this is how it looks, okay? And then if you were to do the same with the carbocation, you would see that most of the LUMO is the empty p orbital, but then some of it's on the adjacent hydrogen. We're talking about this because this gives you a picture of why substitution and elimination reactions compete with each other. I said last time that if a molecule, a nucleophile, attacks on the carbon, you get a substitution product. So I'm going to illustrate that. Of course, yeah, you've seen that before a ton of times. Nucleophile attacks the alpha carbon, dumping electrons into the sigma star, and the leaving group leaves. That's the SN2 reaction, and the nucleophile replaces the leaving group. But if instead the nucleophile or base attacks the beta proton, the carbon-hydrogen bond is broken. Electrons from that carbon-hydrogen bond dump into the sigma star to make a new pi bond, and, the leaving group leaves. And that is what we call an E2 reaction. And the products of that are, again, the leaving group leaves, but instead of the nucleophile being attached to the molecule, you now have a new pi bond between alpha and beta carbons. Okay? So that is the difference between a substitution and an elimination reaction. And the key feature we will see, whether or not we do a substitution reaction versus an elimination reaction, is going to depend on a couple of things. It's going to depend on the identity of the nucleophile or the base, And it's also going to depend on the identity of the alkyl halide, or the molecule with the leaving group. You're going to see that the elimination reaction, the E2 reaction, depends on the concentration of the base and the concentration of the alkyl halide. And you're going to see that an energy diagram for this E2 reaction is going to be very similar to the SN2 reaction. You have starting materials, one transition state, and then products. It's a single step reaction. So we're going to learn what features in the nucleophile or the base bias you towards one of these two options. We're going to see, and we'll see what features in the alkyl halide bias you towards one of these two options. We'll see that sometimes you get preferentially SN2, sometimes you get preferentially E2, and then sometimes you get both, and both outcomes compete with each other. So you need to be prepared for that. Okay, questions about that? Yes?
So for hyperconjugation, we're using that kind of as a reasoning for why it can happen either way, right?
Yes.
But so it seems like, why is it so the lumos or the sigma stars and the sigma are overlapping, and we're just making it kind of count as the sigma star then? Like,
So what happens, maybe I have to go back to here to illustrate it. No, didn't do as good a job there. When hyperconjugation occurs, and last time we talked about it in the context of an empty p orbital and an adjacent CH bond, two things happen, right? A filled orbital overlaps with an empty orbital. So you've got a plus combination when they're in phase, and then an minus combination where they're out of phase. The plus combination looks like this, and this is what happens to the electrons in the CH bond. They spread out a little bit towards the adjacent carbon. So mixing the two orbitals together, here's the sigma bonding orbital, here's the empty the empty p orbital in this case. They mix together, you get the plus combination, which is this one where the electrons move lower in energy, and then the minus combination where the orbital moves higher in energy, and that's this one. This is the LUMO, and this is the one I've been showing you. It's the one that moves higher in energy. What I'm not showing you is what happens to the electrons in the filled orbital. They spread out too, and they move lower in energy. Okay, I saw another hand. Same thing? Okay. All right. Others? Yeah?
Would you say it's similar to a pi bond?
Hyperconjugation is in some ways similar to a pi bond. Yeah. Yes?
In SN1, are there two leaving groups, the hydrogen and the bromine?
So in the SN1 reaction, what I didn't show you is the step that happens before where the leaving group leaves. But that would be, well, shoot. Leaving group leaving. So we will call a leaving group, sorry, I'm struggling to talk today. A leaving group is something that takes its electrons with it when it leaves. The hydrogen is not a leaving group in the sense that it's going to be removed by a base and it's going to leave its electrons behind. Yeah. Okay. Let's do the same thing we just did for the sort of SN2 starting material where sigma to sigma star hyperconjugation is going on. And let's show what's going on with the SN1 intermediate. Here you have an empty p orbital and an adjacent sigma bond. So this is called sigma to p hyperconjugation. I'm just showing you what the LUMO would look like here. It's mostly on the alpha carbon, the positively charged carbon, but some of it is on the adjacent hydrogen. If a nucleophile attacks at the carbon, we get a substitution product. And you've seen that before. If, in contrast, a base attacks at the beta hydrogen, the electrons in that carbon-hydrogen bond will kick down to form a new pi bond with the adjacent alpha carbon, and you'll get this elimination product, this alkene. And we call this reaction E1. It's interesting because the SN1 and E1 reactions have exactly the same first step. So here's the starting material. Leaving group leaves, that's the transition state, the rate determining step. Leaving group leaves. You get a carbocationic intermediate, and then you go down a smaller hill to products. But this first step is the same for SN1 and for E1. So it turns out that the rate laws are identical for SN1 and E1. They only depend on the concentration of the molecule that has a leaving group. Go ahead. I didn't show you the leaving group because I'm only showing you the carbocationic intermediate. Yeah. But we'll do some examples where I'll show you the leaving group. Yes?
I guess it's not clear exactly how hyperconjugation plays into either one being possible.
Okay, so tell me more about that.
I'm just not seeing how it's necessary in order for both to happen. Like, I understand the mechanism of it, but
Yeah,
I guess I'm not understanding why hyperconjugation plays into this.
So what we've learned so far is that any reaction in OChem involves homo of the nucleophile attacking LUMO of the electrophile. And so far what you've learned is that the LUMO is the empty p orbital or the sigma star. So for me to tell you that suddenly the nucleophile is going to choose to attack the beta proton doesn't make any sense unless I also tell you that the LUMO can also be on the beta proton.
Oh.
Yep. Okay, yes?
From this, can we know that it's going to be an exothermic reaction? Is SN1 and E1 always exothermic?
Are SN1 and E1 always exothermic? Well, that's a good question, and the answer is no, because it depends on what the nucleophile is and what the products are. Exothermic versus endothermic for the overall reaction is all about comparing starting materials to products. Now, if you want to talk about the first step of the SN1 reaction, that is always endothermic, that is always uphill because you're breaking bonds. And if you want to talk about the second step where you're forming bonds, either in SN1 or E1, that's always exothermic. So it depends on what you're talking about. Yep. Okay. All right, so what we want to develop now that we're used to the idea that sometimes these things are going to compete with each other is building a framework so we know what to expect and when to expect it. We need to talk about how the nucleophile or base influences substitution versus elimination, and we need to talk about how the structure of the alkyl halide influences whether it's going to be a substitution versus an elimination reaction. So here are a few key principles. First, we've said before that good nucleophiles prefer to attack carbon, so they prefer substitution reactions, and good nucleophiles prefer not waiting for the leaving group to leave. Similarly, we will see that good bases prefer to attack the beta hydrogen, and so they're going to prefer E2 because good bases don't have to wait for the leaving group to leave. Okay, so that begs the question then, what is a good nucleophile and what is a good base? We've dealt with what are good nucleophiles before. Good nucleophiles in general have a negative charge, not always, but often. And they have conjugate acids whose pKa's are greater than 0. So, will you have a pKa table on the exam? Absolutely. Okay, so do you have to memorize these things? No. Now, as I talk to you about them, because I've been teaching the class for more than half the time that you've been alive, I just sort of got it in my head. It's okay if you don't, because I didn't have it in my head before I started teaching the class. You're welcome to use the pKa table to look things up. That's totally fine. We won't take time to do that in class because I like to show off. Is that it? Is that what we're... I'm just kidding. I don't really like to show off. Funny, I don't like to be the center of attention, but here I am in a job where people pay me to stand in front of them and talk to them in 50-minute increments. Kind of interesting. Could I have a job where I just go upstairs and play with my Legos? Would that be, is that a job anywhere? Lego Master Builder, yeah. YouTube channel, no. I don't have the face for a YouTube channel, oh well. All right, well, anyway, got me monologuing again. Right, so things that have conjugate acids have pKa's greater than 0. Let me just give you some examples. For example, carboxylate, whose conjugate acid is carboxylic acid, whose pKa is 4. Also, as an example, and this is not an exhaustive list, CN-, whose conjugate acid is HCN, has a pKa of 9. I'm just throwing some things up here. OH-, conjugate acid H2O, pKa 16. Alkoxides, similar pKa's of conjugate acids. Deprotonated alkynes that are called acetylides also have conjugate acids whose pKa's are around 25. So these are all good nucleophiles. Now, what about good bases? Well, what's the cutoff there? It will turn out that good bases have conjugate acids whose pKa's are a little bit higher, 16 or greater. So of the molecules we've identified as good nucleophiles, you're seeing that some of them, whose pKa's are 16 or higher, are also good bases. So for example, these are both good nucleophiles and good bases, whereas these are only good nucleophiles. Does that make sense? So again, you'll have access to a pKa table, though you'll need to remember the pKa's I told you to memorize, -2 and 16. So alkoxides, acetylides, these are all molecules that are both good nucleophiles and good bases. So for molecules that are good nucleophiles, you're going to be thinking about SN2, but not about E2. For molecules that are good nucleophiles and good bases, you're going to be worried about both SN2 and E2. Question usually gets asked around this point, so are all bases good nucleophiles? And the answer is almost. There is a way to be a good base, but not a good nucleophile. And there are only a few of these. Essentially, the only way you can be a good base but not a good nucleophile is steric hindrance. So as I tried to demonstrate, I don't know how effective it was. Here is an alkyl halide. The bromine is in the sort of red brick color, and the carbons are gray, the hydrogens are white. We're looking down the bond between the alpha carbon and the leaving group, and then adjacent to that alpha carbon on the left and on the right are beta carbons. If we look at the space-filling model, you can see that the alpha carbon is much more difficult to access than the beta hydrogens. And so in general, if you make your nucleophile / base sterically bulky enough, you can make it impossible for that nucleophile to approach the alpha carbon, and you can make it so that the only thing it could do is attack the beta hydrogen. Because as you can see, hydrogens are smaller and easier to attack than carbons are. So, what are some examples of sterically hindered bases that are too bulky for SN2, that is, too bulky for attacking the alpha carbon? One classic example of that is this base called tert butoxide. Often it comes with a counter ion of potassium. Sometimes people will abbreviate this as TBU-OK, and which reminds me of that guy from Phineas and Ferb. Okay, all right? So anyway, tert butoxide is the conjugate base of tert butanol. And tert butanol actually has an even higher pKa than expected for an alcohol. Its pKa is around 19. So you would expect it to be a good nucleophile, but it's not, because those adjacent methyl groups get in the way. It is just too sterically hindered. So that's one of them. There are two others that have abbreviations because their names are too heinous to pronounce. One is called DBN and the other is called DBU. They share this interesting six-membered ring structure with two nitrogens. The doubly bonded nitrogen with the lone pair is the basic nitrogen. And in DBN, the two nitrogens, there's, the second nitrogen is involved in a five-membered ring. And in DBU, the second nitrogen is involved in a seven-membered ring. So, and it's this nitrogen here that's the base, and the presence of the adjacent atoms act as sort of a steric blockade that prevents these from being good nucleophiles. So all of these are poor nucleophiles due to sterics, but they are great bases. Why are they great bases? Because hydrogens are small and they're easy to attack. So for the molecules that are good bases but not good nucleophiles due to steric hindrance, we're not going to be worried about substitution reactions, but only elimination reactions. Yes?
Should we know any more than these four?
Should you know any more than these? I only count three.
Those three?
Yeah, this was the conjugate acid. So anyway, those three, yeah, that's good enough.
Cool.
There are probably others. You'll learn maybe of some more in 352, but for now, that's good. All right, finally, there are things that are neither good nucleophiles nor good bases. And these are generally things whose pKa's are less than 0. Conjugate acids have pKa's less than 0. These would include water and alcohols of basically any kind. Okay? And for these, you're not going to be worried about SN2 or E2. Weak nucleophiles and weak bases have to wait for the leaving group to leave. All right, so those are your considerations. Now, in terms of SN2, we've said it's fast for primary, slower for secondary, no good for tertiary. And we've said that SN1 is prohibitively slow for primary, okay for secondary, and better for tertiary, and that has to do with carbocation stability. Because the first step of SN1 and E1 is the same, what we've learned for SN1 applies to E1. But what we need to do now is answer the question, how does the rate of E2 depend on the alkyl halide structure? So it turns out that for a methyl halide, there is no E2. I'm going to have you think about that for just a minute, and then I'm going to ask you why it is. And I want you to do better than the folks at 8 a.m. did, all right? Pressure's on, right? E2 is slow for primary alkyl halides. It's faster for secondary alkyl halides, and it's very fast for tertiary alkyl halides. So, first, who can tell me why there is no E2 for a methyl halide? Yes? Because the SN2 happens so fast. That is good. That is part of the reason. What else is required for an E2 reaction? Yes? No beta protons. Yep. So you can't do, in the case of a methyl halide, there is no adjacent CH bond. There's no hyperconjugation, no beta protons, no elimination. Okay? Now, so methyl is easy, right? Only SN2 is possible for methyl. All right, let's talk about why the E2 rate accelerates for primary versus secondary alkyl halides. So I'm going to draw a primary and a secondary and a tertiary alkyl halide. And we're going to identify the beta protons. And you're going to see that as we increase the number of carbons attached to the alpha carbon, here we have 2 beta carbons, here we have 3, you see that we multiply the number of beta protons available. So one of the reasons E2 is faster for tertiary alkyl halides is you've got an increased number of options, more beta protons available. So that's the easiest explanation. The second explanation has to do with the stability of the alkene product. So how does the rate of E2 depend on the alkyl halide structure? So what I'm going to do is just show you what the alkene product looks like for the E2 reaction. And I'll label the beta and alpha carbon. So for a primary alkyl halide, you have that kind of alkene. For a secondary alkyl halide, you have this kind of alkene. And then for a tertiary alkyl halide, you have this kind of alkene. And one of the things you notice is that the products are getting more and more non-hydrogen things attached to the carbons of the alkene. We call that being more versus less substituted. And sometimes students are confused by that terminology. A more substituted alkene is an alkene where more of the hydrogens on it are replaced by non-hydrogen things like carbon. So over here we have a di-substituted alkene. Here is a mono-substituted alkene. Here is an unsubstituted alkene. And it will turn out that more substituted alkenes are more stable. And there's a reason for that which we won't talk about in any detail today, but that's a result that you could memorize. The more substituted alkene is more stable, and in the E2 reaction, the more stable alkene forms faster. And that's because the transition state involves a lot of alkene-like character. So the transition state leading to a more substituted alkene should be lower in energy and should form faster. Okay. Questions about that? Yeah.
So substitution reactions will always have two reactants. Sorry, I'm confusing myself. So like elimination reactions will always result in a double bond.
Yeah, elimination reactions will always give you an alkene product. Okay, so let's put it all together. We're going to alter the chart that we developed a couple of times ago to add in the possibility of elimination reactions. On the left, we're going to have a column for a nucleophile or a base. We're going to have things that are both good nucleophiles and good bases. These are going to include things like OH minus and the alkoxides and acetylide ions, things whose conjugate acids have pKa's greater than or equal to 16. We're going to have a bunch of molecules that are good nucleophiles but weak bases. And these are going to include things, this is not an exhaustive list, it's just to remind you, thiolates, CN minus, carboxylates, in general things whose conjugate acids have pK greater than 0 but less than 16. On our list of molecules that are weak nucleophiles but good bases, that's going to be because of sterics, and the classic example of that is tert butoxide. And then we'll also have a final category of molecules that are weak nucleophiles and weak bases. And these are going to include water and alcohols generally. Okay? So you have 4 different groups of nucleophiles. And then we're going to consider how each of these interface with the 3 kinds of alkyl halides, or the 3 kinds of leaving groups we'll be dealing with: primary, secondary, and tertiary. And as we go through, we're going to remember what we learned about the rate of SN2 and E2, and what we learned about SN1 and E1. Before we start in on this, I want to take us back to a place that we were at earlier, where I showed you that the first step of an SN1 reaction is the same as the first step of an E1 reaction. That is, in an SN1 reaction, the leaving group leaves. That's the rate determining step. That's the first step. And then, whether it's SN1 or E1 depends on whether the nucleophile attacks the alpha carbon or the base attacks the beta proton. You're going to see that SN1 and E1 always compete with each other. Now, there are things that you can do experimentally to try to bias the reaction towards a particular outcome. If you watch a lot of Khan Academy videos about OChem, somebody there is going to say, well, if you use heat, you can promote one outcome over the other. For this class, and the way it's dealt with in your text, we're basically always going to show both SN1 and E1 products together. And I'm never going to ask you to tell me whether SN1 or E1 products dominate. You'll simply draw them all, or select them, all of the SN1 and E1 products. Okay? So, with that in mind, let's go through. Now, for a primary alkyl halide with a good nucleophile that's a good base, we said that SN2 is fast, but E2 is slow. Therefore, SN2 dominates. And so you will see SN2 only for a primary alkyl halide with something that's both a good nucleophile and a good base. Okay, you just don't need to worry about the competing E2 reaction there. But because of the fact that SN2 is a little bit slower for secondary alkyl halides, and E2 is a little bit faster for secondary alkyl halides, you're going to see that they compete. And we're not going to worry about which one dominates because you'll expect a mixture of both SN2 and E2 products. You will simply draw both of them. For a tertiary alkyl halide, there's no SN2, so all that you can do is E2. Okay, does that make sense? You're going to consider both things, the structure of the alkyl halide and the identity of the nucleophile or base. Yes?
So in that case, if we're going between SN2 and E2, we're not even going to think about SN1 because it will go.
That's right. When you have a good nucleophile or a good base, you never even need to think about SN1 or E1 because you always have an option. Yep. You've always got an option. Now, good nucleophile that's a weak base, not going to do E2. It can do SN2 with primary and secondary. You can't do SN2 at a tertiary carbon, and it's a weak base, so it's not going to do E2, so all that you're left with is SN1 and E1. You have to wait for the leaving group to leave, and once you do that, you get a carbocation, and you're no longer selective for SN1 versus E1. Now, some students want to know, hey, you told me this is a good nucleophile, so isn't there a preference? Can't the good nucleophile still prefer to attack the positively charged carbon of the carbocation? And the answer is, once you get to that carbocation, it's high enough in energy that the selectivity of the nucleophile goes away, and it's good enough to attack the carbon and to remove the beta proton. Now, for weak nucleophiles that are good bases, this one's really easy. Those can't do SN2, so they can just do E2. Even though E2 is slow, for a primary alkyl halide, the weak nucleophile that's a strong base has no other options, and so it's just E2 all the way. So that one's easy. Finally, for the weak nucleophile that is also a weak base, the only options it has are SN1 and E1. Now, for a primary alkyl halide, I'm going to put the mystery question mark. And in general, we're going to say usually no reaction, but what should we beware of? Yes, beware of the resonance stabilized carbocationic intermediate where you would see SN1 and E1. Yes?
We talked about when something can be a poor nucleophile and a good base. Did we mention when they can be a good nucleophile and a poor base?
Yes, those are molecules that have sort of pKa's between, conjugate acids with pKa's between 16 and 0. Yeah. Okay, so with that, we're now prepared to just try a bunch of examples. And it's better to learn this stuff just by trying examples and seeing what the issues are than trying to anticipate all the possible issues. So let's start easy, and then we'll get a little bit more complicated. Okay, here we go. So a primary alkyl halide and this nucleophile, which if you draw its conjugate acid has a pKa of 25. I just happen to know that. You would need to look it up. It'll be on the table. This is both a good nucleophile and a good base. Because it's a primary alkyl halide, we know that SN2 is fast, but E2 is slow. So we predict SN2 only. That's going to involve backside attack of the nucleophile on the carbon where the leaving group is, and then the leaving group leaves. Had that been a stereocenter, we would have shown inversion of configuration, but because it's not a stereocenter, there's really nothing to see here. And the nucleophile replaces the leaving group. And there we go. Okay, so that's easy. Let's do something where we have to deal with the complications. So here is your starting material. It's got a benzene ring in it. Ooh, it's got 2. And it's got 2 adjacent protons, which I'm going to call HA and HB. All right. Oh, I forgot to tell you something earlier.
Oh, no.
Don't worry about it, because we were going to talk about it again anyway, so this is good. And our nucleophile is going to be CH3O-. So you have a secondary alkyl halide where you know that SN2 is a little bit slower but still okay, and E2 is also okay, a little bit faster than for a primary alkyl halide. And then if you looked up the pKa of the conjugate acid of this nucleophile, you would find that it's not there because it's one you were supposed to memorize, 16. This is both a good nucleophile and a good base. So in this situation, we expect to get both SN2 and E2 products. So you're simply going to draw them both, and on an exam you would select the correct SN2 and E2 products. Now, for the SN2 product, you're going to have backside attack of the nucleophile on the alpha carbon with inversion of configuration. So that would give me the following product, which would be the only substitution product. If you drew the nucleophile here, but with a wedge instead of a dash, that would communicate to me that you don't understand what inversion of configuration is. And if you had drawn both the products with a dash and a wedge, 2 different products, one with a dash, one with a wedge at this carbon, that would communicate to me that you thought the reaction was SN1. So only if you show one stereoisomer with inversion of configuration do you communicate that you know that that substitution mechanism was SN2. All right, let's deal with the elimination reaction. So go ahead.
Just a question, when we're drawing the arrows for the back tag, are you gonna be like specific about like, oh, I guess this is a multiple choice time.
Yeah, so you might have preferred to do something like this, and that's fine too.
Okay.
As long as your product has the right stereochemistry, I'm not going to argue exactly about the trajectory of the arrow.
Okay.
Okay, so one thing I need to tell you about the E2 reaction goes back to the hyperconjugation issue. If we come here and I copy this, you will notice that hyperconjugation, which puts LUMO on the beta protons, requires that the beta proton be lined up with the sigma star. If we drew our Newman projection and drew the beta carbon here in the front with the hydrogen, you would see that it's only the hydrogen that lines up anti to the leaving group. I'm sorry, why is there another BR there? It's only the hydrogen that lines up anti to the leaving group that can participate in hyperconjugation. That is a stereochemical requirement of the E2 reaction. It is just as important as the stereochemical requirement for the SN2 reaction to happen with backside attack. In order for E2 reaction to happen, the beta proton must be anti to the leaving group. There's another word you'll hear in your text that means basically the same thing. It's called anti-periplanar, which means that the 2 blue lines are pointing in opposite directions, but they're in the same plane. Anti-periplanar. the beta proton must be anti to the leaving group to participate in hyperconjugation and to have LUMO on it. So, with that as background, let's zoom in on this molecule. Let's put ourselves in the plane of the page, looking down the bond between the alpha and the beta carbons. And let's just see what we see. So from our perspective in the page, whoops, I don't know why we're red. The benzene ring, which I'm just going to abbreviate as R, is coming out to our right. HB, which is a dash, is going to be down to our left, and HA, which is a wedge, is going to be up to our right. Then for the carbon in the back, the alpha, sorry, I got alpha and beta wrong. Who's going to let me do that? Somebody already has their hand up back there, right? Actually, right, so the benzene ring here should be out to our left. The I, which is a wedge, should be up to our right. And then there's a proton implied but not shown, which I'm going to illustrate there, just down to our right. Okay, so as it is, HB is the one that's anti to the leaving group. So in this conformation, HB is the more reactive hydrogen because it is anti to the leaving group. So when a base removes that hydrogen, and we make the pi bond and the leaving group leaves, let's look at how that requirement for anti to the leaving group affects the product. Whoa, what happened there? Okay, notice that as the pi bond forms, the beta carbon is going to become sp2 hybridized. And that's going to leave the molecule looking like this. And if we were to redraw that, we would see that HA and the other H are trans to each other. The two benzene rings are trans to each other. They are on opposite sides of the molecule in this conformation. They stay on opposite sides of the molecule in the elimination product. Yes?
Not to get nitpicky, but HA and HB look like identical hydrogens to me. So, like, even though they're positioned differently, is it going to give you a different product?
So yeah, if you take off HA, are they going to give you a different product? That's an excellent question. What we will do is keep the carbon in the back at exactly the same location, but now we're going to rotate around carbon-carbon bonds such that HA is now the one anti to the leaving group. I'm doing this kind of fast, so stay with me. We just rotated this around a little bit to the clockwise or counterclockwise direction. If we remove HA now, we're going to get the cis product. So yes, it does matter which proton we remove. If we remove HA, we have to get the trans product. If we remove HB, we get the trans product. If we remove HA, we get the cis product. In this case, both would be formed. Both would be products. And we would expect the trans one to form a little bit more because it's more stable. But on an exam, you would simply select all of those products. Okay, we need some more practice on that. See you Wednesday. Good luck on the exam.